And if you take a look here, let me open this one thing for you 1 second. So you guys can see this equation is known as the first law of thermodynamics equation for open system. So you see this is for steady flow process. When I say steady flow, it means the right hand side goes to zero. Why? Because with the time passing by, the condition inside the system, this is the let me show. This is the system, okay? When the time passes by, the system energy and the mass flow rate remains constant even after 1 hour, 2 hours, 2 seconds, 2 minutes. It does not change. And the right when the right hand side it goes to zero, then the equation becomes like energy power, like it's a rate of energy, which is power going into the device or into the system equals to the rate of energy, net energy coming out of the system. And then this is the first law of thermodynamics for open system. So make sure you understand this open system. So this is the, you will see I will be using this equation for many problems. Plus, I will be using this equation for many problems. And what else I want to mention for the mass flow rate? Mass flow rate. This is also very important. This is also important equation. So I'm gonna show you one conservation. So let me start from the next slide here. Let's do one problem here. I want to show you the difference between the steady flow and unsteady flow system. So if you take a look here, suppose this is a nitrogen cylinder. You might have seen some cylinders. They have certain valves here. When the valves open, the valve opens the gases. They are filled up into the cylinder, and nitrogen is very useful for a lot of purposes, including the HVAC system plus um, cryogenic applications like very low temperature applications. So let's do one problem here. This, let me ask you, is this a steady flow process filling up the nitrogen cylinder, or unsteady flow process? What do you write down in your chat box? What do you suggest your professor? Is it an unsteady flow process or a steady flow process for filling up the nitrogen cylinder? Yes, anyone who is writing down the answer in the chat box? Sarah, Megali, Taylor, Elsie, Han. No, no answer. Okay, this is an unsteady flow process. Why? Because, look, because there is changing of mass flow rate inside the system. This is my system. Where is my system? This is my system. Okay, the mass is changing with respect to time. So let's do one problem, and we will understand more about the unsteady flow process. A rigid tank initially contains air whose density, so the fluid of interest is air, and it has density 1.18 kilogram per meter cube, and the volume of this tank is 1 meter cubed. Okay, the tank is connected to high pressure supply line through a valve. So imagine this is a diagram, and this is a very high pressure supply line. Okay, this is air going inside. Okay, this is mostly air is like nitrogen, so this is air coming inside the cylinder. And when then the tank is connected to a high pressure supply line through a valve, the valve is open and the air is allowed to enter the tank until the density in the tank rises to 7.2. So I would say this is initial density, and the density is 7.2. Determine the mass of air that has entered the system. So if I go back to this slide, if you guys try to understand this unsteady, continuity mass equation. So let me, yeah, this slide is important. So let us use this equation, the first one. So the mass going in minus mass coming out equals to the change in the mass of the control volume, correct? Or of the system. And change in mass is final minus initial. Okay, and the density, if you remember, density equals to mass per unit volume. And I want to know what is mass 2 and mass 1 in terms of density. The mass 2 equals to rho 2 v. I would not give any particular sub for v because this is v is constant. Agreed? Now what is m1? M1 equals to, in terms of density, density 1, volume, which is constant. And now let's apply this everything in equation 1. So I can write down m going in minus 0. There is no mass coming out. This is 0. Agreed? Please type in yes in the chat box if you understood this concept. Why am I setting m out to be 0? That's good. Taylor says yes. Sarah says yes. Magali says yes. That's good. Okay, now try to understand this. We are about to understand the unsteady flow process so that you should be having the certain knowledge, no confusion at all. Determine the mass of air that has entered the tank. So if I apply the equation 1, which is m2 minus m1, this is our answer. Let's solve this equation. M2 equals to rho 2 V minus rho 1. I would say rho 1 V. So V is constant, which is 1 meter cubed. Rho 2 minus rho 1. And rho 2 V is 1 meter cubed. Rho 2 is 7.2. So can you help your professor solving this math equation? What is mass going inside the nitrogen cylinder or air cylinder? 6.02. That's what I have. Is it a steady flow process or unsteady flow process? This is, of course, unsteady flow process. Okay, so let us solve this problem. This is actually an example. So air at 10 degrees Celsius. So the fluid of our interest is air, and temperature T1, it is 10 Celsius, but I will convert this into Kelvin. So 283 Kelvin, and the pressure P1 equals to 80 kilopascals. Enter the diffuser. Diffuser is a device which is shown with this symbol. And if you draw another device this way, this is compression taking place. So it's a nozzle. This is the expression for nozzle where the velocity of the fluid increases at the exit. This is exit, this is inlet. And in terms of diffuser, the velocity of the exit becomes smaller. This is 2 is exit, and the pressure increases as it passes. So this is diffuser. Okay, now if you take a look here, 80 kilopascals enter the engine steadily with the velocities. So the velocity, entering velocity is 200 meters per second. Inlet area. So I would say if you take a look here, it's like a round shape. Inlet area of the diffuser is zero point 0.4, like this, a cross section area. Okay, it is 0.4 meters squared. The air leaves the diffuser with a velocity that is very small as compared to the inlet velocity. So velocity, imagine this is neglected at exit. You have to find out the mass flow rate of air. So mass flow rate of air temperature leaving the diffuser. So we have to find out T2. So let me show you something that if you see temperature related problem, so enthalpy is a very good, if you know enthalpy, you can find out the temperature, suppose H2. So in a in other words, indirectly, if we know enthalpy, we can find out the temperature of the fluid, so of air. So we have to use the table. So m dot m flow rate, if you go to this slide, please take a look at this slide, or m dot, it is rho dV. So I can show you the formula. The formula for mass flow rate, it is equals rho, this is velocity. So what happens, like, this is kilogram per meter cube. The unit of density is kilogram per meter cubed. Unit of cross section area is meter square. Unit of velocity is meter per second. This meter cube is cancelled by these three m values, and you're left with the unit kilograms per seconds. This is the unit of mass flow rate. So let's use this equation. And one more thing, the density can be written as the reciprocal of specific volume. Can I write down like this? A1 velocity V1 maybe I can rewrite this as usually the specific volume symbol, but it's okay. I would understand this is V1. 1 second, I have to rewrite here. This is specific volume, this is velocity. Okay, area 1 is 0.4. This is given 0.4. Velocity 1 is given 200. But specific volume is unknown. Okay, but we do have equation of ideal gas. With the help of ideal gas equation, you can find out specific volume. R for air is 0.287. Initial temperature is given 283 Kelvin, and the pressure P1, it is 80 kilopascals. So if you solve for this, do you get 1.015 meter cubed per kilogram? And if you know this, then can you apply this equation too? So I would write down m dot 0.4, okay, times 200 divided by, and if you solve for this, you should get around 78.8 kilogram per second. You can draw the rectangle around the answer. Do you understand this answer? Now the second question is, what is the temperature of uh, of air at the exit? This is the second question. Okay, let me show you. Can you apply this? We do not know the pressure at exit, so we do not know temperature exit. So this is Very tough situation. We cannot find out temperature at the exit with this ideal gas equation. But first law, thermodynamics, first law, energy or rate of energy going in, rate of energy coming out equals to time derivative of energy of our system. And this is a steady flow. The diffuser, this system has constant mass flow rate as well as constant energy. It's a steady state. So the right hand side for steady state, which does not change with the time, it is equal to 0. And what else do you have? The right hand side is 0 and the left hand side is E dot in minus E dot out. Now, let me tell you this equation. As I mentioned, this equation is very important for first law of thermodynamics for control volumes. So let's use this equation. And let me tell you, there is no heat entering the system. So Q in, I'm just writing down the complete first law equation. This is left hand side, Q dot out. Now, let me tell you, in our situation, diffuser, there is no heat entering or leaving the system. Heats are 0. There is no work being done in or on the system. We do have initial velocity, which is 200, correct? H1 can be found. So this time, so let me write down. This term is 0. This is on the same height, so it's just neglected both sides. So m dot is also cancelled. So you're left with final version of the first law. Final version of first law equals to H2. So what is H1 from the table? So let me open the table. I can share with you the table here. It's a little blurry, but this is A-17 ideal gas properties for air. Temperature T1, it is about 283. And we are interested in these two rows and columns. And after applying your value is 283, and you have to do the interpolation. So H1 minus 280.13. This is the interpolation between the two values, correct? And the right hand side, you have to do the temperature. Pick those values which are corresponding to this value. For this value, the corresponding temperature is 283. Agreed? For this value, the corresponding temperature is 280. For this value, the corresponding temperature is 285. For this one, it is 280. And if you solve for this, you should get 283.14 kilojoules per kilogram. Now, from here, if you consider this as equation 3, so can I write down Can I write down same equation and find out H2? Yes, I can. So look over here. What I'm gonna do here, finding the value of H2. So H2 equals to H1 283.14 plus V1 square, which is 200 square divided by 2. That gives me the value 303.14. And if you take a look, this is the table. So corresponding value of temperature is about 302.93. I'm skipping the interpolation part, which I've already taught you. That's why, to save time, because time is important to complete the curriculum. So T2, for in terms of Celsius, it is 29.93. Do you guys understand how I solved the second part of the same question? The first part was quite easy. That mass flow rate was to be found. The second part was little lengthy, but it is not difficult. First law in control volume contains enthalpy, but in closed system you do not get H, because H is a part of U plus PV. PV over there is zero, no flow. And then from this first law of thermodynamics, you get H2, and corresponding table gives us the value of the temperature. Do you guys understand this question? Please type in yes if you understand this question, or if you have some concern, you can ask your professor. Will you be able to solve such problem in the quiz? The quiz, I'm gonna give you the quiz for this one. Uh, Probably, yeah. What do you suggest? Next week is good? I think so, yes. Okay. You see, this is the energy first law of thermodynamics. Some steady flow engineering devices like jet engine. So you see, if you apply the first law of thermodynamics for these devices, you get this result, which we already saw in example 4. As you can see, for a steady flow, the right hand side is 0, so the rate of energy going in equals rate of energy coming out. So if we have work input for this compressor, then you will write this down on the left hand side. Everything going in will be written on the left hand side. Everything coming out will be written on the right hand side. That way you will be having no difficulty in solving the problem. So we will solve such problems. And the next slide is telling you about another device, which is throttling valve. Throttling valves are heavily used in our HVAC system, refrigeration, and air conditioning, where when the capillaries, this is a very small tube, and when the fluid passes through the small tube, it reduces the temperature, it reduces the pressure as well as corresponding temperature is reduced. The pressure drop in the fluid is often accompanied by a large drop in the temperature, and for that reason, shortening ducts are commonly used in refrigeration and air conditioning applications. The enthalpy is left left hand side is equal to the right hand side, and then for throttling valve, this is true. Then comes another concept of mixing two pipes and like shower. If you are taking shower in, so you need to open the valve for the hot water and for the cold water to have a comfortable temperature, and then you can apply the first law of thermodynamics. Everything going in will be written on the left hand side, coming out will be written on the right hand side, and there is no heat transfer, no work being done, so you will get this answer. So this is the mixing chamber. It is similar to the heat exchanger. Let me show you the heat exchanger which are widely used in our car. In our car, we have radiators where we pour water or the coolant, and if there is a fluid here, the energy is being transferred. So let's see, let's apply, look at this one. The mass and energy balance for the adiabatic heat exchanger in the figure is m dot 1 equals to m dot 2. So these are the two containers. I would say two containers. One is the pipe flowing through the radiator. This pipe is usually very hot. Look at here. At temperature entry level, inlet level 3, the temperature is about 70 Celsius. When it exits, it reduces the temperature. That is the purpose of the radiator, that the high temperature water enters the radiator and it leaves the radiator or heat exchanger, it leaves at a low temperature. And this is the equation. Applying the first law, everything going in would be on the left hand side. So what is going in? Number 1 and number 3 are the entries. Number 1 and number 3 are the entries. Number 2 and number 4 are the exits. They are on the right hand side. You see my point, guys? So this is how you balance the um, energies or rate of energy. Have you understood? This is important, guys. Heat exchanger is an important topic. So you should have clear concept about how to write down the first law for the heat exchangers. If you understood this equation, please type in yes. If not, let me help you if you have any concern. I'll try to explain it to you. Okay, let's apply another application in the pipe and the duct flow. Like if we have a big duct flow, our house is having some ducting, and we have some furnace. You see the ducting system. By the way, my air handler is in the attic. So what happens? We have a big blower, and we have some furnace, gas furnace. So what happens in the winter? We use this system. So in the In the summer, we use the same as like refrigeration coils, evaporator coils, and the same blower is used to pass the air through the coils, HVAC coils, evaporator coils. Okay, let's apply the pipe and duct flow. Let's apply the first law over here. Energy or rate of energy going into the left and the right hand side is the exit. Whatever for this case, let's see. So W dot in, this is on left hand side, M dot H1, this is entry, this is exit, and heat is also exiting system. So whatever is exiting is on the right hand side. Even the fluid itself contains energy in terms of enthalpy. You see my point, guys? So this is the energy which is carried by the fluid itself, other than the externally applied energy. You see my point? This is how you complete the equation of the first law of conservation of energy. Let's come to the next slide, which is related with the unsteady flow. And I initially, when we started our lecture, I gave you this example of the nitrogen cylinder. This is another example. The nitrogen cylinder or any other cylinder which we have to fill in. So how this is also known as the unsteady flow or transient flow or uniform flow. Why do we say uniform? Because at a certain instant, the temperature throughout the container is uniformly distributed. The fluid at any inlet or exit is uniform and steady, thus the fluid properties do not change time over the cross section of inlet and exit. So this is also the unsteady flow process. And let's do the mass balance for the unsteady flow process. Before I do that, I want to remind you that how did we solve this question using the mass balance equation. This is not the energy balance, but this is the mass balance equation. You will use the same thing again over here. Look, for here, the same equation which we used in the first question, which I solved it. And then you will use the second equation, which is the energy balance. And the right hand side is not zero in this case. This is unsteady flow process. The right hand side, you will write down final minus initial energy. So this is theta is a term which we compare, we combine enthalpy, kinetic energy, potential energy. So that's why everything going in is in one bracket, minus everything coming out is in another bracket, gives you the change of the energy of the whole system. See my point, guys? So this is how we apply the first law of thermodynamics on the unsteady flow process. So this is our last slide. What we learned in our slides, this is about the mass balance and energy balance. You learn two main things for open system or control volume. The whole two lectures were about mass balance and energy balance for open system. So let us solve a few problems. This is the problem of a unsteady flow process. A rigid insulated tank is initially evacuated, is connected through a valve to supply line. So imagine this is a tank, okay? And this is a supply line. I would say this is supply line. Let's draw it over here. It's a very big supply. Okay, now this supply line has some steam. You have to fill up the container. This is a valve, okay? When you open the valve, the steam goes inside the evacuated cylinder. Initial, like you see delta M of the system, which is M2 minus M1, correct? The mass balance equation says that mass going in minus mass coming out equals to change in the mass of the system. And in our case, there is no outlet. In our case, initial mass is 0. Look, evacuated cylinder. Initial mass is 0. So M in equals to M2. And this is the mass balance. Energy balance. So energy going in minus energy out is change in energy of the system. And in this case, do we have the now the valve is open, the steam is allowed to flow slowly into the tank until the pressure reaches this. Okay, the pressure increase at edge of the valve. Determine the final temperature of the steam. So we have to find out the final temperature of the steam. So there is nothing, no work is no heat, no work entering or leaving the system, no heat entering or no work on the system or by the system. Okay, so let's apply this equation, which is over here. Energy in equals to energy out. So M energy in M2. Now here in this case, this is M2. M2, this is M in. So remember, when there is a flow, then you will use enthalpy. When there is no flow, it's like a closed system. For closed system, the energy is U2, correct? So M2 is the mass which has entered the cylinder, and it contains the energy U2. And we know that m in equals to m2, so can I cancel this out? So that means h in equals to u2, or u2 equals to h in. So how would you find out h in? You can find it out from the table. So let me show you the table. If you go initial values, look, is connected through a valve supply line that carries. So the initial pressure is of steam is 1 megapascal and temperature is 300 Celsius. Your job is to find out what is the enthalpy at these two state values. So let me open the steam table or the water table at, I would say pressure table is good. 1 megapascal, which is 1000 kilopascal. At 1000 kilopascal, yes. So let me show you at 1000 kilopascal. Now you will tell me that at 1000 kilopascal, the boiling point is, or the saturation temperature is 179, but our temperature is 300 Celsius. So what state is it? What phase is the steam in? Is it liquid vapor, dry vapor, or saturated vapor, or is it a superheated vapor? What do you suggest your professor? Any student? It's a superheated vapor, correct? So at 1 megapascal and 300 Celsius, you are looking at 3051. Please type in yes if you have understood. How did I find out H in? And that is the equal to U2. Okay, guys. So now we have found the two properties. So at the final state, what are the two properties which we know at the final state? So the pressure is 1 megapascal. So you have to find out, and U2 is 3051. So if you know U2 and pressure, and U2 equals to 3051, can you find out T2 from the table? So let's see. If I take a look here, where is my U2? 3051. Somewhere over here. My line is somewhere over here. 3051. Correct? You agree with your professor? So it should be around 450. So you can do the interpolation. So final temperature, I would say 456. Do you guys understand? The the confusing part was that you are looking at U2. Once it enters the cylinder, it becomes a closed system. You will not look at H2. You will look at the U2. And with respect to U2 and P2, you can find out the respective value of the temperature. This was a problem regarding the unsteady flow process. If you understood this problem, please type in yes. If not, and I will explain it if you have not understood it correctly. So let us solve a problem. Do you want to have a mini break or early release? Yes, early release. Okay, I will release you guys early as usual. Okay, let's do this problem. An adiabatic air compressor. When I say adiabatic, what is Q for adiabatic? Is it zero or non-zero? Heat transfer. That's good. And now this is an adiabatic air compressor. This is the entry. This is the exit. And the mass flow rate is not given, but we have the volume flow rate given to us. So if you have volume flow rate, for air and initial pressure is 120 kilopascals, initial temperature is 20 Celsius, and the volume flow rate is 10 liters per second. Determine and exiting state values are pressure at the exit is 1 megapascal and temperature at the exit is 300 Celsius. Find the work required by the compressor in terms of kilojoules per kilogram. The power required by the compressor in terms of kilowatts. This is part A, this is part B. Okay, let's do the energy balance. Okay, energy balance states that energy rate of energy this is a steady flow process. The right hand side is zero. So rate of energy entering equals to rate of energy exiting. And you would see, look, over here, there is, remember this is zero, adiabatic, this, so you are left with W dot in plus this is the first law or energy balance. This okay. and we have to find out W dot in or W in. Can I write down in terms of kilojoules per kilogram? You can also say like W dot in M dot H2 minus H1. Agreed? Now remember in the last previous slides, delta H equals to Cp delta T. This is in Kelvin. And you also learn Cv delta T, but we are not concerned about Cv at the moment, but we will use this formula over here in order to find out W dot in, but initial value is W specific. We are not finding W dot, we just find out. So Cp delta T, and Cp for air from the table, it is 1.0. Cp for air, it is and Kelvin. And delta T is, look, 300 minus 20. 1.018, 300 minus 20. If you solve for this, can you help your professor? Do you get the 285? I just want to make sure that I'm doing correctly. Open your calculators and help your professor. Sarah says 285. Okay, that's good. Now we have done the first part, which is kilojoules per kilogram. The second part says you have to find out in terms of power. So for that, we need to find out what is m dot. Look, m dot equals to, so since we have been given the volume flow rate, so remember, can I write down just to show you that m dot over v dot, or I can write down specific volume. So if you know this, let us apply this. M dot from here would be equal to V dot volume flow rate divided by the specific volume. Agreed? Now at initial state, the specific volume, you don't know, but we can find volume flow rate is 10 liters. So can I write down volume flow rate 10 into 10 to the negative 3 in terms of meter cubes per second. What is this value? We can find out from P1 equation of what we call the ideal gas equation. What is specific volume? R is 0.287 and T1 is 20 Celsius. So I would convert it to 93 Kelvin divided by P1, which is 120 kilopascals. So 120 kilopascals. So if you solve for this is about 0.7. Now guys, we have found V1. You can plug it in over here to find out M dot, which is 0.01427. So if you know this M dot, then you can use this M dot in this equation and you can find out the answer. So look over here, if you do the math, look, you just have to multiply the same work done which you got over here, the same work done. You multiply by m dot in order to get the power. Okay, guys, so I'm going to write this down here, m dot w dot in. Do you get 4.068 kilowatts? Please type in yes if you understood this problem. Sarah says yes. Taylor says yes. Magali says that's good. Okay, this is our last question for the lecture. Okay, let us solve this problem. A pump increases the water pressure. So initial pressure, this is my entry, this is my exit. So initial pressure is 70 kilopascals. Initial temperature is 15. Usually we don't need for Kelvin for this one. I'll just leave it like 15 Celsius. And at exit, pressure has been risen to 700 kilopascals. Water enters at 15 Celsius through a diameter opening. So area is PD1 square over 4. Cross section area, if you take a look here, it is like a cross section area of diameter D1 and exits through the cross section area. I would say the diameter is, if the diameter is given, you can find out the area using this formula, correct? So pi D1 is 1 centimeter. So 1 into 10 to the negative 2 is in meter square divided by 4. And area 2 is pi D2 square, which is 1.5 into 10 to the negative 2 square divided by 4. The question is, determine the velocity of water at inlet and exit. So we have to find out V1, V2. When the mass flow rate through the pump is, so m dot is given. So if we know the m dot, we know that m dot equals to area 1 V1 over specific volume V1. So this is for liquid flow. For liquids are incompressible. So specific volume would be the same one. Will these velocities change significantly if the inlet temperature is? So we have to find out the initial velocity. So that means V1 equals to m dot specific volume or area 1. So area 1 you can find out from here, and so m dot is given 0.5. Look, m dot is given as 0.5. So can I write down 0.5 times the specific volume? Now you have to look into the table. So if I go to the table, temperature table at 15 Celsius, so So I'm interested in this value. At 15 Celsius, our specific volume is 0.001001. And can I write over here 0.001001? So initial velocity equals to 6.37. And you know the m dot is constant. So area 1, velocity v1 over specific volume v1. Area 2, velocity v2 over specific volume v2. This is cancelled because v specific volume is constant for this case. Volume flow rate is constant. So what is my velocity v2? Area 1 velocity v1 over area 2 is about 2.83. The next question states that if the velocity, if the, what will happen to these velocities if the inlet temperature? So we have to see the table. Let's go to the table. 40 Celsius. So 40 Celsius, what is the specific volume? It will change, and we will calculate the new velocity if the temperature is increased. So at 40 Celsius, what is the specific volume? So let's use the same equation here. So I can write down the same equation. Now in this case, I will use this value of specific 0.001008. And when you calculate the velocity for this case, it is a little bit increased. Before that it was about 6.37. This becomes 6.42, which is about 1% increase. With that, I'm going to end this lecture. Thank you guys. You have a good night. Bye bye.